In this lecture, we're going to be introduced to the chemistry of haloalkanes. Before we talk about specific reactions with specific mechanisms and specific opportunities to predict products, what we first need to do is break down how haloalkanes sort of work, I guess, and how we should think about them. So the reactions of haloalkanes are a lot broader than those of alkanes by themselves, because they're bonded to, what we have is an alkane that's bonded to a weird element. Halogens are generally awkward elements for carbon to bond to, especially as you get lower in the periodic table. So reactions of haloalkanes are determined by the halogen in the haloalkane, or just by the halogen atom, I guess. That is to say, if we bond to carbon to some halogen, which I'll abbreviate as X, what we have to recognize is there is a large dipole moment in this molecule. Now, I know that in general, electronegativity moves up and to the right, or increases as you move up into the right in the periodic table, but the halogen atoms are the most electronegative elements in the entire periodic table. So very electronegative. That is to say that iodine is more electronegative than oxygen. So we moved a little bit to the right, but way down in the periodic table. And even still, iodine wins the day over oxygen. So the point is, we have to keep in mind that the halogen atoms are highly electronegative. That creates a large dipole moment. If it's very electronegative, there's going to not be an equal sharing of electrons. And really, the partial charges, delta plus on carbon and delta minus on the halogen, are much larger than we would expect for a typical bond to carbon. Additionally, there is usually a large size mismatch between the carbon and the halogen element. And that's especially true for chlorine, bromine, and iodine. So if you're a carbon element, what we have to, if we kind of compare sizes, just in general, on an order of magnitude, fluorine's roughly the same size as carbon. As we go down in the periodic table, we'll get to slightly larger elements, like chlorine. But as we keep going, carbon is going to stay the same size, but it's going to bond to larger and larger elements. And that's awkward, because remember that a bond results from, an iodine could be bigger, a bond results from orbital overlap between the two elements. And so if one's much bigger than the other, there's going to be some overlap, yes, but it's not good overlap. It's it's not productive overlap. Whereas if you can share electrons across elements that are similar size, you get pretty good orbital overlap. Or if the elements remarkably simple, like in the case of hydrogen, where hydrogen can bond and overlap with carbon atoms quite effectively, actually. So the point is, the size mismatch actually creates a weaker bond between the two elements. That is between C and X. Now, additionally, the bigger the element is, the more awkward it is for that element to bond in a sigma bond fashion. So larger elements do not generally form weaker sigma bonds. And that's a generality to be sure, but it's pretty fair. I mean, iodine bonded to iodine, that's fairly weak interaction. If we shine a little bit of light on it, we can split the iodine in half and it can undergo a bunch of free radical reactions. Same with bromine, and to a lesser extent chlorine. And a lot of that has to do, and there's no difference in electronegativity. It's the elements are the same. So that is most likely due to just the size, the two elements being so big. Okay. Now, with this in mind, we can kind of discuss a general trend for bonds to carbon. So the bond strengths with carbon proceed with the following trend. If carbon is bonded to iodine, that's going to form the weakest bond of the 4 halogen atoms, where bromine comes in second place. Now, chlorine is much stronger when it bonds to carbon compared to bromine. And fluorine itself is even more strong when it bonds to carbon. So the fluorine atom forms the strongest bond. And that's a bit counterintuitive when you think about it, because fluorine's the most electronegative element. If you think of the dipole nature, the dipole moment is so high for a carbon-fluorine bond, but still the bond is actually fairly strong. So it's not just about the dipole nature that determines the bond strength. A lot of it has to do with size mismatch. Now, there's an additional facet to being bonded to a halogen atom. We need to recognize, this is sort of an aside, I guess, but it's very relevant, that due to, and I'll just write the because first before I get to the point, due to the high shell number, that is how far away from the nucleus the valence electrons are, halogens, I'm going to write halogen atoms instead, are able to stabilize atomic charge. Now let's get rid of it easily here. Better than most electronegative elements. Okay, that is what I'm getting at, is that if you see X, one of the halogens, as an anion with a negative charge, this is actually fairly stable. And that's surprising because usually negatively charged things don't like to sit by themselves. Now, of course, this can be countered by some cation to form a salt, but compared to most other elements on the periodic table, they would like to be neutralized with a covalent bond, whereas halogens are happy to sit as negative charges and be countered by some positive charge. So this is a fairly stable anion. And the reason why, sometimes it's related to electronegativity, but it comes down to kind of how close halogens are to forming the noble element configuration, along with, in the case of chlorine, bromine, and iodine, as we go more further down in the periodic table, the we have a lot more protons and positive charge in the nucleus to sort of stabilize this, and the orbitals in general are a lot larger. As we go to higher shell numbers, those orbitals get so big that just throwing another electron in, it's not going to sort of, I guess, have as much electron-electron repulsion as we bring these things closer and closer to the nucleus. Okay. Anyway, that aside, X minus is a stable anion. And what this does is this causes things like HX to be a strong acid. Or if you think about the strong acids, we have HCl, HBr, HI, hydrochloric, hydrobromic, hydroiodic. These are all strong acids. Now, fluorine's a little weird because it's smaller. It's able to to kind of participate in orbital overlap. But the combination of being a stable anion after the H plus walks away, if you recall, this is the acid reaction. In the acid reaction, we see homolysis, where the electrons between the hydrogen and whatever it's bonded to drift towards that other element to give rise to H plus X minus. And anytime you see X minus, just recognize that's a stable anion. We see this with hydrochloric acid giving rise to Cl minus. We see this with sodium chloride, where we have salt's a very stable entity, and it's just a bunch of Cl minuses sitting around with sodium counterions. Okay, so these are strong. I'll just mention that the one you want to recognize as kind of being exempt from some of this is fluorine. So HF is weak, actually. It's a weaker acid. It's very, very dangerous, highly dangerous. The strength of the acid doesn't always mean it's danger. It turns out there are some weak acids that are fairly problematic. I mean, even acetic acid, which is actually natively produced, if you put enough of that on you, it could cause organ failure, that sort of thing. So the strength of the acid can suggest some of the dangers, but it doesn't imply that something is dangerous only because it's, well, let me say it this way. If an acid is weak, that doesn't mean it's not necessarily dangerous. Okay. Anyway, that aside. So X minus is stable. If X has an opportunity to form X minus, it's not as mad as other things would be if they had to kind of sit around as a negative charge. With this in mind, if X would rather be X minus, if chlorine, bromine, or iodine would rather be X minus, chlorine minus, bromine minus, or iodine minus, if something's bonded to that halogen, particularly with a size mismatch like carbon, that's going to produce something that's unstable. So this, let me kind of go right here. This is an unstable sigma bond because X minus is stable. And I've mentioned this before, but in general, CBr is the most useful. It's got a nice balance of stability and reactivity. Like it's not, the bond is not so stable that it doesn't do anything interesting, as in the case of carbon and fluorine, carbon fluorine and carbon chlorine. These are too stable to react. It's often their reactions are less predictable and more often than not boring. They just kind of sit around. Whereas carbon and iodine, as I mentioned, this is too reactive. The bond is so unstable that we try to do chemistry with these types of things and they just fall apart. Many times they undergo spontaneous homolysis, for example, or they can be induced into homolysis, which is not necessarily where we want to go so early in the semester. So the CBr one is most useful, and that's something that we're going to be talking about a lot. Now, having set us up to recognize that the halogen atom is stable as a negative charge and actually forms a relatively unstable bond with carbon, let's talk about the general reactivity of haloalkanes. Now, in general, the X, which is our halogen, leaves. And so it's often called and this is an important term, a leaving group. Now that's a very important term, and it really helps us understand the chemistry. So these halogen atoms are more often than not willing to depart from the molecule as they do some sort of chemistry. So it's a leaving group. Well, what does that mean? Well, let's tackle this issue first. What I want to do is say, okay, let's identify the leaving group. So let's say I have this molecule, and I wanted you to circle the atom, which is the leaving group. You would circle the bromine. The bromine is the leaving group. Now this, okay, this looks fine. I mean, you just look for the halogen atom, the thing that's not part of the typical bond line structure. And so many people are like, yeah, I could do this on a few of these elements. Does Willoughby just want me to circle the halogen atom? Well, sure. Now, the reason why we're doing this exercise, as trivial as it may seem at first, you just look for the halogen, you circle it, is because down the road, the molecules get a lot more complicated. Like, let's say we've got something like this, and we've got some molecule here, and this, and then we go to here. What I want you to be able to do is look for the leaving group. Now, the leaving group is going to be a halogen in most cases. So halogen atoms are the leaving group. Okay, so that's a skill I want us to be able to do. Look at complicated molecules, circle the leaving group. The leaving group is the halogen atom. It's just something I want us to kind of get ingrained with, I guess, if I had to rephrase. Okay. What we're going to do next is look at the general classes of reactions. In each of these classes of reactions, we're going to see that the halogen atom leaves or is replaced or is just pushed off of the molecule. So the classes of haloalkane reactions, there are kind of two broad categories. They are substitution and elimination. In the case of substitution, the X is replaced to form X minus. In the case of elimination, the X is pushed off to form X minus. Okay, so in both of these, I've said what happens to our halogen atom. The other thing I want us to broadly look at with substitution is we form a new carbon, a new bond to carbon, and we kind of form a new alkane in a sense. With elimination, we replace the CX bond with a double bond to a neighboring carbon, which means we form a CC double bond, which according to lab 6 is an alkene. So we have an alkane being formed by substitution reactions and an alkene being formed through elimination reactions. Now, what these sort of look like is if we have some CX bond, we are going to react them with, I like to write it as nu minus, and this nu minus replaces X, and we form a new bond to nu along with X minus as a byproduct. Okay, so nu replaces X. In the case of elimination reactions, which is on the right, we take CX, but we need to consider actually a carbon adjacent to the CX, and that carbon needs to have a hydrogen, and we're going to let that react with a base. Now the base is going to react as bases do by grabbing a hydrogen. In this case, it's the hydrogen with a star to give rise to an alkene plus our base having been neutralized with the H and X minus. Okay, so that is a quick breakdown of the types of reactions that haloalkanes do. For the remainder of, or for the next several lectures, we're going to look in detail at each of these reactions. So if you don't follow, that's fine. We'll get there. We are going to look at the mechanism in details. I think the mechanisms are a little bit more fun than the chain reaction mechanism. So if you didn't like that, this will probably be better. But I think it's really healthy to have an overall perspective on these mechanisms, to recognize what types of products we'll see. And with substitution, we're kind of replacing the X group, the halogen group, with something else, which for now I'm calling new. That doesn't really make a lot of sense, but we'll get to that. In the case of elimination reactions, we're actually pushing the X off to make a carbon-carbon double bond. We're not replacing it with a new atom. We're just making an additional bond to the carbon. It doesn't have any room for the halogen anymore. And the halogen does what leaving groups do. Leaving groups leave. So we recognized in both of these processes, the X leaves as X minus. And that's going to be very consistent for all of the reactions that we look at for haloalkanes. One thing sometimes I like to talk about is how do you make this new functional group. So we've talked about how this is a new functional group. We talked about how to name it. We talked about the general classes of reactions it undergoes, along with some of the properties, like the halogen atom forms a weak bond to carbon. But another thing that could be really helpful to include would be a discussion of how to make these things. Where do they come from? Haloalkanes are very important. One way to make them, there are many, but one way that we know how to make them is through free radical halogenation of alkanes, which we just looked at. So in the spirit of keeping the lectures on the shorter end, to make sure we won't repurpose the notes or, kind of reproduce the notes. I won't go through that reaction again because we just spent several lectures going over it. But to suffice it to say, if you want haloalkanes, a good way to make them is through free radical halogenation of alkanes. Okay, with that, we'll call this lecture good.